Hello, next topic is Secure Design Principles by Nikola Luburic.
Hey guys. Well, I'm going to start this talk with a short story about Susan. Now, a few years ago, Susan was the chief security officer at a large corporation you might have heard of called Equifax. She's retired now, but the reason for her retirement has nothing to do with age. Susan retired because of the absolute disaster that was the Equifax data breach. Now, as you may know, this attack happened about 2 years ago. It was a multi-phased attack where the attackers managed to retrieve about 140 million records, personal data related to Americans. So almost half the population of the States. This attack succeeded because Susan and her team failed to apply some simple secure design principles. So, at the start of this talk, we'll go examine the broader scope of secure design principles and see how they address software security, how they fit into this secure software engineering. After that, we'll look at 5 sets of secure design principles which are applicable to almost anything that you can make today, from various software to protocols to building design. And then finally, and hopefully the most important question by the end of this talk, how can you start practicing these design principles in your everyday software development? So, let's start. We want to have secure software, and as software engineers know, and thankfully security engineers require, this is not something that's easy to do. We need to address security throughout the software development lifecycle. We need to specify the security requirements. We need to examine the threat model. Who wants to attack us? Which assets do they want to harm, and how do we protect them? Then we start designing. We need to construct a secure by design solution. So this is the first point where these secure design principles enter our story. When you're performing design activities, you always want to keep these design principles in mind so that you can create a secure by design solution. Then we move on to code, where we want to perform some static code analysis, some security code reviews to make sure that there are no code level vulnerabilities, that there are no flaws in your implementation. Arguably, the most important part of our secure software engineering is the verification and validation. So we need to see if there are any vulnerabilities left in our solution. We need to test, to perform penetration testing, security testing, to see if the secure design principles were followed, if there are no secure coding mistakes, and then basically, if these guys don't find your vulnerabilities, you know who will. Once we have a potentially shippable increment, it's time for release, so maybe we'll deploy, perform some secure delivery and deployment activities, and of course, all of this needs to evolve. We need to manage the work that we do. We need to follow the threat landscape to see which new tools come up and to integrate them into our security development lifecycle. So now, let's focus on the secure design principles. Who are the people working in software development that should be aware of this? Well, as I mentioned, of course, if you're a designer of software and systems, you need to address security during your design. You need to plan for security, plan the security controls, the security work, so that it gets done. But it doesn't stop there. When talking about implementation, we really can apply these secure design principles at the code level as well. So when talking about design, we have this macro level, the architecture of the system, of the software, but we also have the micro level, the code design. And this is where we can apply these principles to write better code. And of course, the security code reviews will review the code that we write and make sure that it follows the design that we specified. Our testers are affected as well because we need to verify that these principles were followed. They will examine our attack surface. They will see if our access control is correct, and this is something that we should plan in the design. So let's look at the principles we will examine today. We'll start with defense in depth. And the idea here is to apply multiple security controls to our solution so that we can remain secure even if that control fails. Let's look at an example. So we have some file integrator service application. It's communicating with some external file storage. Maybe this is our system, maybe it's a business partner, it doesn't really matter. All that matters is that we're receiving important data from this external file storage based on which we can perform some business operations. And then we store it somewhere locally. The idea is that we have an attacker that wants to modify this data, compromise its integrity, so that they can harm our system. They will change the data, it will become corrupted, and then our system will crash, or maybe it will continue working, but with false data, it doesn't really matter. And we want to protect this data. A possible attack can be on the communication channel itself. So we introduce a security control, we introduce secure file transfer protocol. Job done, right? Well, not if we're talking about defense in depth. We need to ask the question, what if it breaks? What if this secure file transfer protocol doesn't work, doesn't provide us with the security that we need? Well, another related question might be, why would it break? Why can't we trust this control? Well, security controls fail for a number of reasons. We can have a bug in the implementation of the SFTP. You create software, you make bugs all the time. Well, why wouldn't these guys make the same mistakes as you? Technology can be vulnerable. We've seen it a large number of times, even in well-known security controls that we are supposed to trust. Then we might misconfigure this software. Maybe the SFTP is secure, the implementation is okay, but we don't properly configure it. Our IT personnel forgets to set some certificates or maybe set the appropriate configuration. So we have a vulnerability. And finally, the security control can be improperly used. We might think that we're secure, but we don't really understand the security control, and then we're applying it to no great effect. So defense in depth tells you to ask this question: what if it breaks? Is there anything else that provides security for me? In this case, we might introduce file signatures, so digital signatures, to guarantee the integrity of our data as an additional security control. Now, if the SFTP fails, we still have the digital signature as a fallback. If it fails, hopefully the SFTP won't, and if both fail, well, that's just very bad luck. So, another example, we have a similar situation where our application is communicating with an external service. And we have an attacker that wants to spoof our business partner to pretend that it is this service so that he can supply some data for us. Once again, maybe he wants to compromise our system in some way. The question is, how do we authenticate this business partner? And an easy solution is to have some endpoint addresses that our service is targeting, and to make sure that they are targeting our business partner. But of course, this isn't enough, because the addresses can be spoofed. The attacker might perform some DNS poisoning or something along those lines, and the request and communication can be redirected to his malicious service. So we introduce cryptography once again. We have some certificates for authentication, and now we have some security that this business partner is the right one. But of course, this doesn't really solve our attack surface. What if the attacker is inside our business partner system, and then he can channel the attacks through these legitimate communication channels? So validation is an obvious solution here. We want to validate everything that's coming from our business partner, and to make sure that no rubbish gets introduced into our system. What happens if the validators fail? What happens if our application crashes? We might decide to introduce a service dedicated for this validation, so that it crashes if there is some advanced attack vector coming here. And similarly to the internal business app, in the previous case, we will introduce all of these security controls to have this multi-layered defense in depth. All of this is at the software level so far, right? But what about the network? What about the hardware, the operating system? Well, we should consider these controls as well to have really a multi-layered, multifaceted defense in depth, where an attacker that manages to break a single control ideally won't have any other advantage. He won't gain anything by compromising our SFTP, for example. But let's at least try to reduce the advantage that he does get from this successful exploit. Moving on, attack surface analysis. Now, this is more of an activity than a principle, but it is still somewhat related to software design. The idea is to always keep in mind where an attack can come from, and then to limit these avenues as much as possible. Of course, we want to have the system perform the business functions that it's supposed to, but nothing else. Here, let's look at an example where we have some user communicating with an application which is in turn communicating with some data center. A set of SQL databases, some NoSQL databases, files, whatever. And we have some files with which the application is communicating, and an attacker that wants to compromise our data center. He wants to destroy our data, modify it in some way, or simply read it to sell it on the dark web. The question for attack surface analysis is, where does the attack come from? And we call this attack surface mapping. Well, in this case, the attack can come from anywhere. This is the first assumption that we should make. Start from everything and then focus. But what should we focus on? Well, trust boundaries can help us here. We can determine where it is likely that an attack can come from by examining who has access to particular resources in our system. If we have a browser application, then pretty much, if it's publicly available, pretty much everyone from the internet can target these endpoints here. What about the communication between the file system and the application on the same machine? Well, it's not really easily accessible, right? So we can see what is inside our scope and what is implausible, and reduce some of these concerning areas to focus only on the important parts for this attack surface analysis. So we would want to protect the communication and endpoints facing the internet. We're concerned with files here because insiders might compromise them, and so on. Once we've mapped the attack surface, we can, let's just summarize this part. Where can an attack come from? The interaction points are an obvious attack surface. All your data stores, data flows, especially those between multiple machines. What should we focus on? Data arriving from less secure zones, especially those zones that have a near infinite amount of attackers, such as the internet. And what is out of scope? Well, of course, we have a scope defined by our team. We will try to secure the components made by our team, but we should really write down the assumptions that we make. Maybe we say that we're not concerned with protecting the OS. Okay, but write it down. Because when another team member comes with more experience, he might tell you why this is a mistake and that you should be concerned with the OS, even though you're a web developer. Now, after we mapped the attack surface, we can start reducing it. The first question is, how can we limit the access to this attack surface? So when talking about access control, the most important question is, who can access this? Who can access these files? Who can access these endpoints? Who can access the data center? Which applications? Which users? These are the questions that you need to answer. Once we've limited the amount of attackers that can access our resources, the question is, how can we limit their opportunity? And what do I mean by this? Well, in this case, we have some temporary files, right? How long are they available? Is this something that we will delete in a minute, in a day, in a week? An attacker might not take over our system by compromising these temporary files, but he might learn something interesting. He might read some errors, he might steal some data. If we don't really need to have these temporary files available for a month, why not delete them after a day or even sooner? For the application, we can ask the question, how frequently are functions used? Do we need to have all functions available during the night? If this is an internal app, we can maybe shut down the system. But more importantly, are all the functions that are available in the software actually used? Is there some set of functions that nobody uses or that a very small % of our users use? Maybe we should remove those because they open an attack surface and we don't really get much benefit from them. And of course, this is related to deprecated code as well. Do you have some dead code that nobody is using, nobody is maintaining? It might present an attack surface that you completely forgot about. In general, this is good advice for software development, not just for security, but also for security. For the data center, we can ask the question, how much data does the application use? How frequently does it contact it to retrieve data? As we'll see with Susan, it can be quite important to limit the amount of data that's available from the database, to minimize it to only the necessary amount of queries, commands demanded by the business. Once we've limited who can access the endpoints, who can access the files, once we've limited how long they are available, when they are available, the question is, how can we limit the attack vectors that can arrive through these controlled channels? And this is basically input validation when talking about the application layer. So the questions that we should be asking is, how does the application, how does the data center handle malformed inputs? So this is attack surface reduction. For limiting the attacker's access, we will examine the next set of secure design principles related to sound access control. For the attacker opportunity, we should consider the time frame when data and functions should be available, the frequency, how much availability should we have. Once again, some measurements to see what is the expected amount of queries and so on. And really, should we even have that data and functions available to begin with? For attack vector limitation, input validation, something that you should really perform for all data coming to your application. In general, we can always limit the type of data, the length, possibly the character set or values which are arriving. But we might also perform some specialized validation for specific data sets, data types. So we're talking about SQL injection, some prepared statements. XML injection, XSD validation, and so on. So let's look at one more example for attack surface analysis to wrap this up. And we will examine at a low level of design this time, where we're looking at a single application, a Spring application, a .NET application, it doesn't really matter. We have some HTTP endpoints which are communicating with a data access layer, a Spring repository, for example. We have an attacker that wants to compromise the data, and now we're examining a single part of the attack surface, namely the HTTP endpoints. How do we perform attack surface analysis here? For one, we look at all the endpoints. What are all the functions that are available to this user? And then for each endpoint, we examine all the inputs, all the places where the user, or rather the attacker, can send an attack vector. So we examine a single HTTP request, and here we have an obvious input in the query parameters. But a somewhat less obvious input are the headers, especially when you have custom headers. These are headers which your application is processing at some point, and then the attacker can send attack vectors here, as was the case in Susan's system. So we would go on to map the attack surface by examining all of these endpoints. For post requests, put requests, we would obviously also look at the request body, and this would be the mapping of our attack surface. The reduction, access control, input validation, and so on. Crucially, understand where the attack can come from, and then limit these avenues as much as possible. Sound access control is next, as I already mentioned earlier. And this is essentially a set of 3 security design principles that we will look at. The idea is to restrict access to all objects across the system at all levels, at all times, as much as possible. Support the business and nothing else, but also minimize the power a single individual has. So let's look at this. The first principle we're looking at is complete mediation. And this is basically check everything always. For the example from a few slides back, we should be asking the questions, who is this user that's communicating with our application? Do we check all the requests that he or she sends? And who has access to the files? Are all requests checked? Is all access tracked? For the data center, likewise, who can access this data center? Is it only the user app? Is it some administrator? Is it everyone? But also, who can access the particular databases here, the tables? Do we have some control for this? We should, and this is least privilege. Basically, allow access only for the business and nothing else. So, if we have 3 sets of users here, maybe we'll distribute a set of functions to the first set, another set to the second, and the third set to the third. For the data center, maybe we will have multiple applications interacting with the databases. Are we controlling which application can access which data? This is least privilege. Minimize the amount of access. Finally, for separation of duties, we want to limit the amount of power a single individual has and to have them be accountable for all their actions. Going back to the defense in depth example, we can ask the question, who has access to these data stores? Now, if a single person can configure all of these endpoints and certificates, that person can also point our system towards a malicious service. Are the changes to these data stores, given their criticality, logged? Can we at least make the guy pay for ruining our system? And a related question, who has access to the log files? Is it the same guy? Well, obviously he can hide his tracks then. So essentially, sound access control is an extension of the attack surface reduction to limit access to only what is required by the business and nothing else. Secure mechanism design is our next topic. And here we will also examine a set of 3 secure design principles. The idea here is to conceptualize a simple design. In general, we want to have simplicity in our software, but for security controls, this is especially important. Complicated design will make finding vulnerabilities more difficult. So we want to simplify this to make sure that we understand how our security controls work to avoid their malfunctioning. Also, we want to avoid shared states as much as possible. If we have a state that is shared between multiple users or multiple programs, then an attacker can corrupt this shared state and trigger the attack on these other users or programs. And finally, to have a secure design, we need to fail securely. Failure will happen, and we need to be prepared for it. So let's look at the design principles that make up this set. The first one is economy of mechanisms, and as I said, it's related to simplicity. To elaborate on this, let's go back to the application example. Now, the question here is, where do we perform input validation? We said that there's data arriving at our HTTP endpoints. It might be in the headers, it might be in the query parameters, it might be in the request body. At what point do we validate this data to make sure that the attacks do not trigger? One option is at the source. As soon as possible, when the data is arriving at our endpoint, let's validate it as much as possible. The next option is at the sink. Right before the attack triggers, this is the place there where we want to discard all the attack vectors. The third option is somewhere along the way between the source and the sink. So where do we validate? Well, the answer is both at the source and the sink. We perform source security checks for two reasons. One of them is that this helps protect all the sinks. The attacker might be supplying an attack vector which will harm our logger, or maybe some XML parser in the business logic. If we remove these attack vectors at the start, these attacks won't go to the database, they won't go to the parser, to the logger. We can remove them as soon as possible. Another benefit is that we're removing rubbish quickly. We don't have this malicious, malformed data traveling through our system being processed in some way. We're discarding it at the start. So if we're doing these checks at the source, why do we need to perform some checks at the sink? Well, two reasons once again. The first is that here we can prevent specific attacks. If we're talking about SQL injection, and we can't really whitelist the sensitive characters that can perform this attack, well, we can create prepared statements at the sink. If we have some XML parsing, we can perform XSD validation at the sink at the parser. But also, what if we have multiple sources? What if there are sources that are out of our control? By validating at the sink, we can defend even against these poorly validated sources. So let's go back to the design principle. Make simple designs that enforce security consistently. What we should definitely avoid is to have some custom validation somewhere in between. Rather, focus always on the source and the sink so that people can know this is where we expect to see security controls. And we do really need the source and the sink so that we can have this consistency, so that we can validate all the data and not just have some part of it be validated. The next design principle that falls into this category is least common mechanism. And the idea here is to minimize the amount of shared states that exist in our software. Let's look at an example with a web application where we have some global variables which our application is loading into the browser. If an attacker can compromise these variables, he might be able to place some cross-site scripting attack. He might be able to do this through the front-end application, or maybe as a malicious administrator that has access to the configuration files, he inserts this attack vector. We should definitely minimize the amount of global variables and ideally control access and perform the necessary validation to all the shared state that must exist. Looking at another example, say we have an application running on a machine. It has access to the file system, and we have another application here which has a vulnerability. The attacker might be able to exploit this application to compromise the file system, or maybe so he could delete the files that are required by our secure application. He might clog up the memory, take up all the threads, the processor, and crash the whole machine. So to solve this, we invented virtualization, right? We invented containers to separate these applications, and if the vulnerable application is exploited, well, at least our other application won't suffer. Finally, secure failure. So our software will crash. It's inevitable. All software crashes. What happens when our software crashes is a security concern. How will we fail? What happens if a single function crashes or a service? Does this mean the end of our complete solution? Well, let's look at an example where we have a user with some application and we have some authentication logic where the user is accessing the application. He first must log in, and the proper access control checks must be performed. And we also have some auditing logic. So everything the user does needs to be logged so we can have non-repudiation. A user makes a request and the authentication logic fails. Does the operation continue? Does the user perform the action that he wanted? The business logic is fine, but this authentication logic does not work. Obviously, we don't want this to happen. We want to block the operation, and we call this fail closed. If this fails, everything should stop. What about the auditing logic? What happens if we can't log the action? Maybe the file system is full, our log files need to be rotated, something along those lines. Do we stop the operation? Well, it depends. We might fail openly. We might say, okay, these are some less critical applications. We don't expect serious security issues if these actions aren't logged. So maybe we will say, okay, continue on with your operation. But if this is a sensitive action, if we're talking about some banking transactions, obviously we would want to have everything working properly. The question here is very similar to defense in depth. What happens if a component, a service, a function fails? Should our process stop? Will our system even recover? These are the questions that we need to address and to know how our system behaves when it does crash. So for secure mechanism design, simplicity, minimize shared states, and fail securely. The final secure design principle I want to talk about today, and this will be a short one, is related to secure security controls. Now we have all of these security controls. They are performing some encryption, some authentication, some validation. But are we sure that they are working correctly? Are we sure that they are implemented properly? This principle says that you should thoroughly investigate all the security controls that you're using to make sure that you are aware how to use them, how you can configure them perhaps to be insecure, and how they can fail you. Let's go back to the first example of this talk, the file signing. Now, we have this digital signature mechanism, but the question is, how do we implement it in our code? Do we implement our own algorithm? Probably not. We can fail at every step along the way. Do we take a proven algorithm, something that people claim is secure, take the design, and then implement our code for it? Well, slightly better, not really great, not terrible, but still, we can introduce code-level vulnerabilities here, right? So we choose an existing implementation. We find a provider of this function and then integrate it into our solution and use the API. But it's not really that simple. Who can we trust? Who are the trustworthy providers? Is this some GitHub project with 2 stars, some student made for his bachelor? Well, obviously this is not a good choice. But if it is something offered by our operating system, maybe it is a good choice, or a renowned provider of security controls. We select a provider, and then we should ask the question, what are the configuration options for this control? Is the function secure by default? I don't have to provide any parameters and it will work. Maybe, probably, if it's a good provider, but don't count on it. You need to be aware of the configuration options to realize what can go wrong, what can be misconfigured. Because if we have a misconfigured security control, we might not have a security control at all. And finally, are there any known vulnerabilities or issues with this implementation? Something that really should be applied to all of your third-party dependencies, be it tools, databases, the operating system, or the plethora of libraries that you're using. Check to see if there are any known vulnerabilities on the CV, on the NVD. Examine if there are any problems that you should be aware of that can be exploited. To sum up, when introducing security into your code, don't make the Google query and then copy and paste the first link from Stack Overflow. There was actually a study where the guys examined the amount of vulnerable code that's posted on Stack Overflow and how frequently it is found in Android applications. It turns out quite a lot. About 30% of applications that have some security code had vulnerable security code because they pasted it from Stack Overflow. And the irony is that in the comments, people stated, this is vulnerable code, don't use it. But the developers didn't care. Don't be that guy. So for secure security controls, always investigate. Perform your due diligence. You're introducing this security control, make sure it is introduced correctly. Now, let's wrap these 5 sets of design principles up through Susan's story. Let's examine what happened at Equifax 2 years ago. So, in this story, we have some guys that want to get rich. This is your standard attacker. He is examining the internet for services that have vulnerabilities. At this point, there was a publicly known vulnerability for Apache Struts, a framework for building web applications not unlike Spring. And Equifax, of course, used this version of Apache Struts. So the attackers were examining the internet, and lo and behold, they found this vulnerability at a corporation that's serving hundreds of millions of people. The vulnerability in question in the Apache Struts framework is the lack of input validation for HTTP headers. And this is where the attackers were able to deploy the attack that took over the machine. It took over the machine because the web application was running under administrative privileges. So they managed to perform remote code execution here. The attackers started examining the system from this point and quickly discovered the database containing administrative passwords. These passwords were not encrypted. They were not hashed. Nothing was protecting them, not even basic access control. They took these passwords and then they started accessing all the other systems. Quickly, they retrieved millions of sets of data related to personal information. About 140 million, slightly over that, people got their data stolen. Of course, there was no network segmentation here. There were no query limits on the database, so attackers could perform tens of thousands of queries with no penalty, with no alarm. There was actually a security control in place that could have seen all of this, but it was broken. There was a network monitoring tool that could have raised an alarm, but it wasn't working. The certificate expired 10 years ago, and nobody changed it. Yeah. So basically, Equifax sucks at security. All of this is basic hygiene. All of this is one of these design principles. So for the HTTP headers, this is slightly cheating, but it is an insecure security control. You're depending on this framework. It does provide a number of security options out of the box. You really should be updating it. But how could have Equifax known? Well, the Department of Defense sent an email way before the attack, telling them, hey, maybe you have Apache struts in your infrastructure. You should probably check it. And they said, nah, it'll be fine. They didn't check it, and then the data got stolen. For the web application, having full privilege over the machine, obviously we don't have sound access control design. For the administrative passwords, no access control, and really no defense in depth. Where's the cryptography for the passwords? Network segmentation, obviously some form of access control. Query limits, attack surface reduction, limiting the opportunity that the attacker had, and broken network monitoring. Well, insecure failure at best, but broken security control at the core. Okay, so these were the 5 sets of secure design principles that can apply to all software, really. And there's only one question left to answer. How can I introduce this into my organization, into my team? Obviously, this 1-hour talk won't cut it, right? At best, I gave you a map of where to look. So you need to read a lot. First of all, you can start with this NIST publication. In its Appendix F, it covers a broad spectrum of secure design principles, a lot more than I covered here today. Not all can be applied to all systems, but you really should check them out to see which are applicable for your context. Now, these design principles, really like any software engineering principles, it's not something you can read and then I know it. You need to search for examples, you need to examine them, research them, you need to reread the definitions, experiment. It takes a while to learn. After that, you can examine these 2 books. They are concerned with an activity of design review that checks to see if your design is actually secure. We call this security design analysis. So, and Shostak and Schoenfield can really help you develop this attacker mindset that's required for security design analysis. Finally, when you've digested all of this, it's worth examining the complete security development lifecycle to see how your design principles can interact with the rest of development. You can access the freely available Microsoft ebook regarding their SDL, but core software security is slightly less known, but still a valuable catalog of information. Now, after you've digested all of this, after you've done your preparation, you can start thinking about introducing this to your organization by performing a proof of concept on the software you're developing. And here you have 2 options. You can go solo and try to work over-time, maybe grab some hours from work to start introducing this security into the design of your software. The obvious benefit of this is that you're only working with your time, right? You don't need to get other people involved. You don't need to ask for money, basically. But the flaw is that you're really overfitting yourself. For one, only you are becoming the expert here, and for 2, you might not, well, more minds are better than one, obviously. The second option is to get team buy-in, where you will get some resources from the team, from your product owner, and start introducing this probably more slowly, but also probably more efficiently. And then hopefully you have some good results and you can move into the continuous improvement phase, where you'll focus on increasing the efficiency and quality of your security design analysis, and maybe after some time go into marketing to show how secure your design is. So it's not an easy journey. And hopefully I've given you this map that can help you with these design principles. But if you need more help, so as a supplemental or maybe alternative approach, feel free to contact me. I have a small team of people working with me on this, so maybe we can set some collaboration up. Now I can take your questions. Or did I just kill you? Well, okay, guys. If you need a refresher, I'll be here all day. So, red shirt guy, there's 4 of us in this room. Hopefully, you'll find me. The only one with the beard, though. So, feel free to approach me, ask anything you like regarding the secure design or the security development lifecycle. Thank you for your attention.